Lecture 6b of Differential Equations in Linear Algebra is about linear transformations in 2 dimensions. A very beautiful geometric subject. I think you're going to like it. I do want to make this lecture shorter than 6a was. That was a pretty long lecture, trying to deal with the details of Mathematica usage to set us up for the rest of the semester. I think I can be shorter here, though at the same time I'm going to go through the content pretty quickly. Let's skip this slide. Let's now look at linear transformations in 2 dimensions. I've got 3 slides that have some descriptions, essentially some definitions. Then I have a bunch of examples that we're going to look at, geometric examples of linear transformations. What is a linear transformation? Well, at the most basic level, you should realize that it's a function. Okay? Linear transformations are functions. That's the first thing to realize. I'm calling it a 2-dimensional linear transformation. It's a function whose domain is 2-dimensional space, denoted R2. What is that, R squared? No, it's not R squared. It's R2, which is notation for 2-dimensional space. A little more precisely, it's the set of all points that are ordered pairs, that could be thought of as points in a plane. It's the 2-dimensional plane. Set of all ordered pairs where x and y range over the real numbers. Now, typically we view this in terms of rectangular coordinates, but as I've emphasized, we don't have to do it that way. It still, in a sense, represents a 2-dimensional space. To itself, the domain is 2-dimensional space. The codomain is 2-dimensional space. I'm going to use that word codomain instead of the word range, because the word range is, well, it's kind of ambiguous. It means different things to different people. So I'm going to call it the codomain, the target space, 2-dimensional space. The inputs are all of 2-dimensional space, and the outputs are in 2-dimensional space. It involves a system of linear equations in this form that defines it. U equals ax plus by and v equals cx plus dy, where a, b, c, and d are constants. In the system of equations, the independent variables are x and y, and the dependent variables are u and v. The a, the b, the c, and the d are constant. Alternatively, instead of thinking of it as 2 independent variables and 2 dependent variables, we can sort of mash things together. We can think of a single independent 2-dimensional variable, x comma y. The ordered pair is the independent variable. And the corresponding dependent single 2-dimensional variable, the ordered pair uv. Should we imagine these ordered pairs as being points? Usually, yes, that's the case, but not always. Sometimes we'll imagine these ordered pairs as representing vectors. When they're representing points, we usually call them coordinates, the individual parts of the ordered pair. When they're representing vectors, they are typically called components or components, depending on the way you pronounce it. Note that in these equations, there are no pure constants. No pure constants. No plus d or plus e plus f if e and f were numbers. There's a good reason for that. This is actually important. Okay? It's not that we couldn't define linear transformations to have constants if we wanted to, but we'll see there's a good reason for that, for not including them. Notation. To emphasize the oneness of the ordered pairs, and to emphasize that this is indeed a function, we often give the linear transformation a name, a function name. We could call it f, but a more traditional thing to call it is t, for transformation. But it is a function. I could call it f or g. It's more traditional to use capital T or maybe capital L. It's another option. We emphasize the domain in the codomain, also called the target of t, but I'm not going to use the word range, with the following notations. T colon R2 arrow R2 means t is a function, really, with domain R2, codomain R2 as well. The domain is the set of all 2-dimensional ordered pairs, points, vectors. The set of outputs are two-dimensional, though the function is not necessarily onto. It's possible that not every point in the codomain is a possible output, and we will see one example like that. Another way this is written is like this, where instead of having a t and a colon, you put the t above the arrow. Okay? We might also write the inputs and outputs as ordered pairs, points, like this, for example. On the previous slide, it was a system of equations. U equals ax plus by, v equals cx plus dy. I'm writing that now, that system of equations, system of two scalar equations, as one point equation or vector equation. uv equals t of xy. And use that kind of language. U comma v equals t of x comma y. T is a function. And that function is defined by this formula. The first coordinate or component of the output is ax plus by. The second coordinate or component is cx plus dy. But we might prefer writing these things as column vectors, like we've done with vectors. Or maybe even mix them together like this. Ignore these spaces here, they're not supposed to be there. The output vector, column vector, uv, is t of the input column vector xy. And the same formulas produce that output. Or maybe we do a mixed one and write t of xy here, where this is now an ordered pair. A point, if you will, instead of a column vector. You might also write the inputs and outputs with vector notation, either with little arrows or half arrows, kind of like this, or with boldface, like this. So capital U and capital X represent vectors, column vectors. You could use these little, I don't know if you can see it very well, these little half arrows above the U and the X. Kind of hard to see unless you zoom in close. Or you could use boldface, especially if you're typing something, to emphasize the oneness, again, of the inputs and outputs. And that you can think of them as either points or vectors. Whatever is more convenient, whatever is more helpful as far as how you're applying these ideas is the best way to view it. You can also visualize linear transformations. How? Is it an ordinary kind of graph? You could make a pair of ordinary graphs, though they would be multivariable calculus graphs. But it's more traditional to visualize these things as maps. Mapping is the official name, map for short. Not the usual kind of map. Here's the United States, here's Minnesota, here's New Jersey. Not that kind of map. A transformation as a map. What is that? Why are we using the word map? I think essentially it's because of the kind of pictures that we make. Sometimes are reminiscent of physical maps. Mapping or map in mathematics is just another name for a function, just like transformation is another name for a function. And to help us visualize the mapping, we look at certain sets of inputs and see what happens to them under the mapping. What do the corresponding outputs look like, either as points or vectors, more commonly as points. We can consider the image of the set A under T to be the set of all outputs as the inputs range over A. Okay, I use the word range. It's an okay word to use here, but it doesn't mean the same thing as range means in other situations. With set builder notation, if the set of all values T of X as X ranges over R2. I've used set builder notation before with curly braces. In lecture 6A, you'll have to watch it. I'm still going to sometimes call these curvy braces, and sometimes I'll call them curly braces. I think curly braces is the more official name for these things, but I kind of like curvy braces. The vertical line means such that. What is this saying? Are we plugging A into T? Well, kind of, but A is a set, so it's not literally an input for T. This is called the image of A under T. It's just shorthand notation for this set. Okay, the set of all outputs. By the way, I'm using lowercase x here for the vector, whereas in the previous slide I used uppercase. It doesn't matter. Okay. Sometimes I'll use lowercase, sometimes I'll use uppercase. If A is all of R2, the entire plane, we could also write the total image of T itself as the set of all outputs as you range over the entire plane. An alternative notation for that, this whole thing, is ImT, the image of T itself, so to speak. You could also call it the image of R2 under T, just like this was the image of A under T up here. But it'll be convenient for us to use ImT in certain situations in the future. Big idea here is we might be able to understand T better by understanding how it transforms various kinds of sets. We're about to consider examples. We can, in a sense, even start with a geometric description of the behavior of the mapping, which is what we're about to do for sure, and then create a formula from that. So I'm about to show you examples described geometrically, and we'll look at the formulas for these things. Though that's not a guarantee that the formula is obvious. Sometimes it's obvious, sometimes it's not. You have to have some experience with these things. The examples are going to make these concepts more clear. Okay? You ready? Here we go. Example 1. Reflection across the horizontal axis. As a mapping of points / vectors and as a mapping of a set of points A. So I'm about to show you actually 3 pictures. The first picture is how we think of it as a mapping of points. The second picture is how we think of it as a mapping of vectors. And the third picture is going to be an animation showing how a certain set of points gets transformed under this reflection across the horizontal axis. Here's the first picture. So you see a plane, a rectangular grid in that plane, graph paper, that's rectangular coordinates. You see kind of weird labels, x/u and y/v. And this point is labeled xy, and this point is labeled uv. But uv equals x negative y? What in the world's going on here? What you need to imagine is that before the mapping is applied, we got a given point like this point with rectangular coordinates 3, 5. 3, 5. Those are its x and y coordinates before we apply the mapping. After we apply the mapping, after we reflect the point across the horizontal axis, it's like we have a new plane with a new coordinate system and axes labeled differently, u and v. It's one way to imagine it, and I think it's a useful way to imagine it, even though it's a bit confusing. It's like the labels for the axes change. And, well, if this point has xy coordinates 3, 5, and I reflect it across the horizontal axis, the rectangular coordinates of this point are 3, negative 5. X negative y. 3, negative 5. Those are the uv coordinates, which are still, it's still the same kind of coordinate system. It's still rectangular coordinates, but just different labels, u and v instead of x and y. And by the way, I can also call this t of xy. I didn't put the t in there. I actually will in the next picture, but I could call this t of xy equals x negative y. It's the formula, so to speak. And the outputs I'm giving new names to. I'm calling them u and v. Other points also get reflected across the horizontal axis. This point here, for example, would get reflected to this point here. So if the xy coordinates were negative 4, negative 2, the uv coordinates of the point it gets mapped to right up here are going to be negative 4, positive 2. The y coordinate gets negated to become positive. What if your point starts out on the horizontal axis to begin with? It would have to stay there. And the x, y, and uv coordinates would be the same numbers. any point that starts on the horizontal axis here under this reflection stays where it is. We can also imagine mapping vectors as arrows. This vector x, y, written symbolically as a column vector, but graphed as an arrow, gets mapped to this vector, which I call t of x, y, which I certainly could write x negative y for, and I could call that uv as well. I made this with Mathematica and it didn't let me put a negative sign in the text mode. I don't know why. So it's like the arrow gets reflected. But wait a minute, I thought with vectors it didn't matter where you put the arrow. That's true. However, it's useful to put the arrow in certain spots to interpret what you're seeing correctly. So we're going to put these arrows to be based at the origin, with the tail at the origin. What if the vector were at components negative 4, negative 2, this arrow? Its image would have components negative 4, positive 2, this arrow. And vectors that are horizontal to begin with would stay horizontal and would stay equal to themselves under the reflection. The origin, by the way, gets mapped to itself, and the 0 vector gets mapped to itself. And here is a way to visualize it as a mapping of a set of points. This red parallelogram right there, A gets mapped to its image, T of A, which is blue. The in-between steps, by the way, are just your own imagination. They're not literally it's not literally what's happening, okay? You know, the math in terms of the formula is just a static thing. But we can bring it to life by imagining the mapping this way. What's the lambda? Don't worry about what lambda is. It's just an animation parameter. I just let it go from 0 to 1. To see the starting set in the xy plane get mapped to the ending set in the uv plane by reflecting. We can even consider images of wild and beautiful sets, like how about the butterfly curve? You've ever seen this curve before? Isn't that pretty? So it's called the butterfly curve. Equations for it can be found by Googling it. You'll find equations on Wikipedia, for example. It's drawn with parametric equations involving sines and cosines, as you might imagine. But we see it get reflected across the horizontal axis as well. It gets transformed from the red set of points to the blue set of points under the map. This mapping, again, has this formula. T of xy equals x negative 1. Let me introduce a couple vector variables. Oh, what should I call them? Capital U vector equals, say, AB, and capital V vector equals, well, okay, let's change it. Let's call this capital X vector, and this one capital Y vector. I'm using A, B, C, and D, just like I did when I first started talking about linear transformations, but this is not the A, B, C, and D from up here. The A would be 1 and the B would be 0 here. The C would be 0 and the D would be negative 1 for the formula up here. These are not the same things as those. It's just generic two-dimensional vectors. What is T of x plus y? Talked about adding vectors before. You add component-wise. If I add these two vectors, I get a column vector whose first component is A plus C and whose second component is B plus D. If I now plug that into this formula, what kind of output do I get? Well, the first component gets mapped to itself, so to speak. The A plus C stays in A plus C, but the second component gets mapped to its opposite. So I have a negative B plus D in parentheses here, though of course then I can distribute the minus sign through the parentheses. Let's see what happens when we do T of x plus T of y. T of AB plus T of CD. Looking at the same formula here, replace the x with A and the y with B in this part to get A negative B. These are A's, by the way, not 9s. And then plug in CD, you'll get C negative D. And that will simplify to the exact same thing. These two things match when you now add these. That's not a coincidence. It's called the operation preserving property of T with respect to vector addition. There's also an operation preserving property of T with respect to scalar multiplication. If alpha is an arbitrary scalar, you should check that this is true. And these are the key properties that make this transformation linear, and are also the key properties that are the reason we don't add pure constants in the equations. We want these equations to be true, because it ends up being a useful way of thinking about it. On to more examples. How about a reflection across the 45-degree line to the origin? Oops. Okay, now I'm just going to show one picture in these other examples. I'm mixing the point view and the vector view, using both points of view in the same picture. And there's not going to be an animation because it made the file too big for the other examples here. So the green line is the 45-degree line to the origin. For any given point or arrow, x, y, which I'm taking to be this point, whose coordinates would be -2, 5, I reflect it across the dashed green line, which means I draw a point over here such that the line segment connecting these points makes a right angle, is perpendicular to the green line, and the distance between the red point and the green line and the blue point and the green line are the same. I hope it makes intuitive sense, and of course if you look at the actual coordinates at this point, that you just swap the coordinates to do that. So -2, 5 gets mapped to 5, -2. 5 here. 5, -2. You can see it in the picture. Whether you think of the inputs and outputs as points or arrows, and I could write these things as column vectors too. What about a point or arrow down here? Let's go ahead and write it as a column vector. Components -2, -6. It gets mapped to a point or arrow. That's going to be right about like this. -6, -2. Swap the x and the y around. This is supposed to be straight, by the way. That's supposed to be a straight vector. The line segments connecting these points here and here is perpendicular to the green line, and these distances here and here are the same. So the formula in this case is that UV equals T of xy equals yx. You swap the coordinates or components. That's what the formula is telling you to do. And once again, the operation preserving properties are going to hold. If this will hold, you should double check that. And the one with an arbitrary scalar in front will hold. Let's go ahead and fill out the details for that one here. The alpha represents an arbitrary scalar. I need to multiply the scalar times the column vector by doing it component-wise. So I have alpha times A and alpha times B. I swap those components for the output. I get alpha times B and then alpha times A. If instead I did alpha times T of x, I'm going to get the same thing in the end. These two things match. Operation preserving property of linear transformations. Expansion or dilation is another word you can use by a factor of 2. Moves points twice as far away from the origin along the same ray. or stretches the vector by a factor of 2. It points in the same direction, but it's twice as long. The formula is uv equals 2x, 2y, which I can also write as t of xy. Pointer vector over here, say. Nicer. Is going to get mapped to be, once again, twice as far from the origin, along the same ray from the origin. So the image vector is going to be there, or the image as a point is going to be right there. -3, positive 1 gets mapped to -6, positive 2, and that means I drew it wrong. Like that instead. What kind of applications do these things have? They will have application to our main use of linear algebra in the course, change of coordinates. It's a very important application. But they have more, you might call them hard-nosed applications as well. For example, to computer graphics. Linear transformations are useful for designing computer graphic systems. We can rotate. I picked 90 degrees about the origin. Could have picked 45 degrees or 60 degrees or even 273.2 degrees. This is not so obvious, but what happens is your domain points gets mapped to a new point where the coordinates are swapped and a negative sign is put in front of the first one. So if this point has coordinates, which it looks like it does, 5, 2, the rectangular coordinates of this point are then -2, 5, which you can see is accurate. I better not try another one exactly because, well, okay. Maybe it'll be okay. Yeah, it'll be okay, never mind. My input vector looks like this, say, components -6, positive 3. It's going to get mapped to a point or an arrow where you swap these and you put a negative sign in front of the new first coordinate. It'd be -3, -6. -3, -6 right about here. That's the rotation in that case. It is a 90-degree rotation, it turns out. Okay, not completely obvious that this would be the formula. uv equals t of xy is -yx. You should check some more points to make sure it seems like it's working. I can check the operation preserving part here, but I won't for sake of time. On to example 5. I believe there are two more examples, examples 5 and 6. Shear transformation is not like shearing sheep. It's shearing in the sense of making, I don't know how to describe it. It's like you take a building and you're pushing the top down and so it slants. That's a shear transformation. An arbitrary point xy, which I happen to pick on the vertical axis here, gets mapped to a point with these coordinates. If the input point was not on the vertical axis to begin with, say it was here, well, that one's got, let's write it as a column vector, components 1, 3. It's going to get sheared to the right as well. As far as figuring out where it goes to, just use the formula. So the image point for the first coordinate or component, you need to add these, so 1 plus 3 is 4. And the second one, it stays the same. 4, 3 is what it needs to get mapped to. That right there is what this red arrow gets mapped to under this shear transformation. The formula in this case, in terms of column vectors, you add the coordinates or components for the new first component, and you keep the second component as is. In terms of ax plus by and cx plus dy, a is 1, b is 1, C is 0, D is 1. You can verify operation preserving property for this one too. Projection onto the horizontal axis. It's not a reflection, it's a projection. It's like we have light source out at infinity. We did talk about projection vectors before, lecture 5b. Applied it to finding the work done by a force. But now we're not, no physics application here. Imagine a light source off at infinity in the vertical direction and down at negative infinity in the vertical direction, shining light rays perpendicular to the horizontal axis. Give me an arbitrary vector or point. What's its shadow under with those light rays that are perpendicular to the horizontal axis? The shadow of this red arrow is this blue arrow. The shadow of that red dot is that blue dot. No matter what your initial pointer vector is, you get a new pointer vector that's on the horizontal axis. The second component is 0. The formula here, in terms of column vectors, is T of UV is UV equals T of XY. First component stays as it is, the second component becomes 0. This is an example where the image of T is not all of the plane. This function is not onto. The other examples actually are onto. The image of T, the set of all possible outputs of T, is this horizontal axis. All these points or vectors get mapped onto it. And that happens when they're down below as well. This one gets mapped to this one. So even though the domain is two-dimensional, the image as a set is one-dimensional, though in terms of our coordinate system in the plane, you can think of those as two-dimensional points because they're sitting inside a plane. So that's a bit different. These are all good to remember for the future here, and we will be reminding you of these things. This is the last slide, I believe. The operation preserving property, if we want to write it down more carefully. In each example, it was emphasized that the transformation is operation preserving. Probably the hardest one to check seemingly at the beginning would be that shear. That might be seemingly the hardest one to check. You should check it. This means the following. It means T of x plus y equals T of x plus T of y for all vectors x and y in R2. This means in is an element of is the more official. And T of a scalar lambda times x, I used alpha before, is the scalar times T of x for all vectors R2 in the plane and all scalars lambda, all numbers lambda. More succinctly, you can combine these into one expression. T of alpha x plus beta y is alpha T of x plus beta T of y for all vectors xy in the plane and all scalars alpha and beta that are real numbers. These properties, which you can either think of this way or this way, they're equivalent to each other. This is one equation that captures both of these equations. Either way you think about it, these are key properties of linear transformations that are going to be essential for the course, okay? It might not seem like they'd be essential, but they really are. A lot of the properties of linear transformations are based on these. In fact, this is the definition of what a linear transformation is. So, I guess it's not the last slide. So make sure you pay attention to that. Here's the last slide. It's a little preview. Lectures to come. This is pretty cool, though it's hard to understand. Linear transformations don't have to be visualized as mappings. They can be visualized as something called vector fields. What's a vector field? I'll describe it quickly, though it's kind of a hard concept, at first at least. Say we got a linear transformation. Vector fields are functions like this. This is an example of a vector field, at least, where you want to think of the inputs as being points. Notice the point notation here. And you want to think of the outputs as being arrows, vectors. But we're not going to draw the arrows all based on the origin. Here it's going to be more useful to draw them based at the input point. That's going to be the tail of each vector that we draw. At each point x, y in the plane, we attach a vector. Here are a couple examples. This example is the same as the reflection across the horizontal axis example. This example is the same formula as the reflection across the 45-degree line through the origin example. But we're not graphing them as mappings of points, like the butterfly curve point, set of points. We're graphing them as what are called vector fields. What does that mean? It means that, for example, at this point right here, xy equals 4, 1. The output, according to this formula, is you want to think of it as a vector. I couldn't draw it as a vector here, but I could draw it like that. You want to think of it as a vector whose first component, x, is the same as the first coordinate of this point, 4, and whose second component, negative y, is the opposite of the second coordinate of this point. The output, t of 4, 1, that point is the vector for negative 1, a vector with, excuse me, that doesn't look right. Oh, I got the point wrong. 1, 4. 1, 4. T of 1, 4 will be the vector 1, negative 4, horizontal component of 1, that's a negative 4 there, horizontal component of 1, vertical component of negative 4, which is what you see when you look at this arrow right here. Horizontal displacement, 1 unit from 1 to 2, first coordinate of this point to first coordinate of that point. Vertical displacement of negative 4, from 4 down to 0. First coordinate here, 4 down to 0 is the second. Second coordinate here, 4 down to 0 is the second coordinate of this point. Vector fields, this one's even harder to understand, but I would encourage you to do it. Vector fields are kind of reminiscent of slope fields. And in fact, they are related to slope fields, and that's why Mathematica uses vector plot to make slope fields, because it also makes vector fields. One final comment I should make is the origin as a dot gets mapped to itself under the linear transformation, so the image arrow is just a dot as well. And that is the last slide. Thanks for watching.